Greetings, fellow humans. Today I want to talk to you about analog sensors. Digital sensors are great if you want to know binary information, like if something is on or off, up or down, in or out, etc. But if you want to know how many millimeters, how many grams, degrees, cats, whatever, you might want to use an analog sensor. You can use digital sensors to measure amounts of stuff too, by dividing up what you're measuring into little binary buckets and slapping a digital sensor on each bucket. But at that point, you are losing the precision of any values between buckets. Analog sensors provide very precise measurements, and instead of a snapshot, you get a continuous range of values over time. But it's important to point out that if you're looking at a reading, and that reading is a number, then that value has undergone digitization at some level somewhere along the way anyway. The mere act of taking a snapshot of the value at some moment in time and turning it into a number puts it in a digital bucket with an implicit level of granularity. But I digress. The Raspberry Pi is a wonderful platform for slapping sensors on things and for all manner of DIY, home automation, monitoring, IoT devices, you name it. And it's got all these wonderful GPIO pins, which are quite literally general purpose pins that can be used for input or output. But the Raspberry Pi does not have an analog to digital converter, or ADC. And as such, it can't really read an analog sensor directly. There are, however, many microcontrollers with built-in ADCs, like, for example, the Raspberry Pi Pico. And in a moment, we'll take a look at Adafruit's QT Py ESP32 Pico, which also has a built-in Wi-Fi and analog pins, and it's awfully cute. But first, let's take an intermediate step and look at an ADC chip in detail for a second here. This is the MCP3008. It's an 8-channel 10-bit ADC, which means it can analyze 8 analog signals simultaneously, and it can translate each signal into a 10-bit digital value. You can communicate with the MCP3008 using SPI, and SPI is really cool. If you're not familiar with it, you should definitely look into it, but it's outside the scope of this video. For our purposes, we just need to know which pins on the Raspberry Pi we need to connect to the ADC in which order and whatnot. So we connect one side up to the Raspberry Pi. There's 2 live voltage pins, 2 ground wires, and 4 I/O pins to do the heavy lifting on this side. And then on the other side of the chip, we have 8 sensor pins. Now, a typical analog sensor has a connector with 3 pins, a positive, negative, and data. So our little breakout board here pulls each of the 8 sensor pins off into this header over here with a positive and a negative pin. So we can just connect our sensors up using standard hardware, right? Plug that bad boy in. We're good to go. So the go-to sensor for demonstrating an ADC is usually a potentiometer, because V equals I times R. So if you adjust R with constant I, it makes the V go up and down. But I prefer eTape for demo purposes because it does the same thing. It's just bigger and there's water involved. So much more fun. Anyway, basically when I move the sensor up and down, the water level rises and falls relative to the eTape. And the code just outputs a raw number between 0 and 65,535, because that's how digitization works. And converting that number into a meaningful unit is as simple as y equals mx plus b. Now, as cool as this is, and we are talking nerdtastic fun for the whole family here, you probably don't want to connect this monstrosity to your sump pump for home monitoring purposes. We live in a silly time when buying the component parts of a thing and building your own is more expensive, takes longer, and yields a lower quality product than just procuring the thing outright. So for monitoring your sump pump, you're probably going to want something more like this. This is the QT Py ESP32 Pico from Adafruit, and it's currently my favorite little microcontroller. Built-in Wi-Fi uses a bunch of the analog pins, but we really only need one of them. And the built-in Wi-Fi also means we don't need a Raspberry Pi on location, so to speak. All we need is the USB-C for power and 3 wires to run out to the eTape sensor. So that's what we did.